Okay, I want to finish up talking about kernels and images um, as objects before we get to talk about their properties a little bit more. But a nice thing about kernels and images is that they really have a lot to say about whether a function is one-to-one or onto. And just a reminder what a one-to-one function is. So the technical way you can think about it is if you know that the function sends v1 and v2 to the same element, that means that v1 and v2 must be the same element. And what that means in terms of a diagram, so this is your v and this is your w, then each element in v gets mapped to a different element, w1 or maybe tv of 1, and this is w2 or tv of 2 in w. So things never go to the same element. So that's one-to-one. And onto means, so it means for all elements in your codomain, everything, there's always an element of your domain of v that gets mapped to w. So there's always, so if this is our w here, any element you like here in v, you can find something that always maps to w for every element in your codomain. So that's one-to-one and onto. And basically, one-to-one and onto functions are characterized completely by the kernels and images of the functions. And by functions, I mean linear transformations. So onto functions are exactly the ones whose image is the entire codomain. And one-to-one linear transformations are exactly the ones who have a trivial kernel, whose kernel is just the zero vector. And you always need the zero vector in your kernel because you know that the zero vector in v always gets mapped to the zero vector in w, so you know the zero vector is always in any kernel. So let's look at this. We'll prove the onto bit first. So this is an if and only if. So we need to show that if t is onto, then the image is everything, and the other way around. If the image is everything, then t is onto. So let's do that first direction here. Let's prove that if t is onto, then the image is everything. So we have this onto transformation t, and we're going to pick some w in our codomain. Since t of v equals w for some v, that's because t is onto. So that's literally the definition of being in the image. So you can see that the image and onto are very related. And the other way, let's assume that the image of our linear transformation is everything in our codomain. So if we're assuming that, we're going to pick something in the image. What does that mean? Well, if it's in the image, that means that there's some element v that gets transformed into w. If you put it into your function t, or your linear transformation t, you get w out. But you know that the image of t equals w. That's what we're assuming here. And that's the definition of t being onto. So t is indeed onto. That's great. And to be completely truthful, it's not quite surprising at all that the image and onto are so closely related because they're basically the same concept. They talk about finding something in your domain that can get mapped to things in your codomain. But the next one that we're going to do, that a one-to-one function is exactly when the kernel is 0, that might be a little more surprising. So let's show that next. Okay, here, let's let our linear transformation be 1 to 1, and we want to show that the kernel is indeed the 0 vector. So what we're going to do is we're going to pick something in the kernel and show it's the 0 vector. It must be. So forget this. I don't want to include that, so we'll just pretend like that isn't there. So what we're going to do is we're going to pick something in the kernel of this transformation. We know something exists because 0 is definitely in there. We know 0 is in every kernel. So if it's in the kernel, that means when you plug it into your transformation, you get the 0 vector. But remember, we also know an element in the kernel is the 0 vector in V. We know that that has to get mapped to the 0 vector in W. And remember, what does a one-to-one function say? That if two things get mapped to the same element in your codomain, the element of the domain must be the same. So this tells us that V and the 0 vector in V are the same thing. So this tells us indeed V is the 0 vector, and maybe I'll be a little more clear here. This is the 0 vector in V. And maybe a little diagram would help for this as well. So if this is V and this is W, so we automatically know that the 0 vector in V gets mapped to the 0 vector in W. That's with any linear transformation. And we're picking something else in the kernel. So we're picking some element V that gets mapped to 0. It's because we're picking it in the kernel. But for things to be 1 to 1, we can't have this situation happen where two vectors get mapped to the same vector. So the only way that this can happen is if V and the 0 vector are the same thing. So V is indeed the 0 vector. Great. So we know that all one-to-one functions have a trivial kernel. Now we need to show that all functions with a trivial kernel are 1 to 1. And just to be clear, by function, I mean linear transformation. Okay, so let's do the other direction. Let's assume we have a transformation that has trivial kernel, where it's just the 0 vector in the kernel. Okay, so what we're going to do is we want to show that T is 1 to 1. So we're going to pick two vectors, V1 and V2. That might be the same vector, but might not be. But we definitely know that we're picking them so that they get transformed to the same thing. So let me draw a similar diagram down here. So here's our V, here's our W. And we're picking two vectors here. Let's say V1 and V2, where they both get mapped to the same vector. So this is both T of V1 and T of V2. And the whole idea, we want to show that if the kernel is just the 0 vector, then the only way that this can happen is if V1 and V2 are actually the same vector, that these lines actually must overlap. Okay. So we understand the setup. Let's get to showing this. So remember, we have that this is a linear transformation, so we do want to use that. So we're going to try and get the 0 vector involved here because we're assuming something about the 0 vector. In fact, that the kernel is just the 0 vector. So if T of V1 equals T of V2, we can subtract off T of V2 from both sides, and then use the property of linear transformations to together. So this is the same thing as t of v1 minus v2. So we know that is the zero vector. Well, what's that tell us? That tells us that this vector, v1 minus v2, gets mapped to the zero vector. That's a definition of being in the kernel. So v1 minus v2 is in the kernel. But we're saying that the only vector in the kernel is the zero vector. So that means that v1 v2 minus v2 must be the zero vector. And we can just add v2 to both sides to show that v1 must be v2. So we started with t of v1 equaling t of v2, and we showed that v1 must equal v2. So that's a definition of our function being one-to-one. And the second fact that one-to-one linear transformations have a trivial kernel, that's very useful to show that a function is one-to-one. It's a lot easier to show that the kernel is trivial a lot of times than it is to show that the function itself is one-to-one. Okay, so let's look at this particular function. So this function goes from m by n matrices to m by n matrices. And the way it works is we pick some invertible matrix that's m by m, and for any matrix we put into our function, it just multiplies it by u transpose u. So first of all, let's check that this makes sense in terms of dimensionality. So we know that u is m by m, and a is m by n. So we know we're taking an n by n matrix and we're doing something to it. So let's make sure the dimensions line up. This is m by n. We know u transpose is m by m. We know u is m by m. So it looks like all of the inner dimensions match. So this makes sense, this multiplication makes sense, and we'll end up with an m by n matrix, which is exactly what our codomain is. So this looks good. All right, so let me zoom in here. And maybe I'll leave as an exercise for you guys to show that T is indeed a linear transformation. So that's something that you guys can show on your own time, but we're going to show that it is both one-to-one and onto. All right, let's start with one-to-one. And remember, let's use our idea that that's the same thing as showing that the kernel of this linear transformation is just the zero vector. In this case, since we're in our domain is m by n matrices, that the zero vector is the zero n by n matrix. So let's set that up, and then let's see if you guys can do this yourselves. So we want something where T of A is the zero vector. So we want to let A be in the kernel of T. So that means that T of A is the zero vector. But we know what T does. We're told T takes A and it multiplies it on the left by U transpose U. And we know that that equals that zero matrix. So maybe pause the video now and see if you can figure out how to show that indeed A must be the zero matrix. So pause the video and try that. Okay, if you haven't figured it out, I'll give you a hint. Remember that U is invertible. the determinant isn't 0. And remember, what that means as well is that U transpose is invertible. So the product of these guys is invertible too. So if you haven't figured it out, pause the video again, see if you can figure it with that hint. Okay, now that we're back, we're going to use the idea that U transpose U is invertible. Since both U and U transpose are invertible, the product of those guys is invertible. So I'm going to take this entire expression, and on the left, I'm going to multiply by U transpose U, whatever matrix that is, inverse. So I'm going to multiply the right-hand side of the equation on the left by U transpose U inverse as well. And you can check that the dimensions make sense here. This is m by m, so its inverse, of course, is going to be m by m. So all of our multiplications work. If we multiply anything by the 0 matrix, we of course get the 0 matrix. And we know that a matrix inverse times the matrix itself just gives you the identity matrix. So they just cancel off, give you the identity matrix, so we're just left with A on the left-hand side. So we've done it. We've shown that the kernel is indeed just the 0 matrix. We picked something in there, A, and we showed that, well, it's 0. It's the 0 matrix. So we've done it. Okay, now let's show that indeed this is onto. So we want to show that the image is indeed all of m by n matrices. So we're going to take something in the codomain, which is m by n matrices. This is onto. So we're going to let's say, we already used A, and let's let it be B. B sum m by n matrix. And we want to find that T of something equals B. So maybe pause the video now and see if you can figure out what that is going to be. What m by n matrix I can plug into our function where it gets evaluated to B. Okay, if you need a hint, remember again that we picked U to be invertible. That's the thing with this linear transformation, that it multiplies it by U transpose U, where U is an invertible matrix. The determinant isn't 0. So think about if there is a way that you can have some sort of an expression in here involving B where the U transpose U is going to get canceled out. Okay, so let's think about this. So we want T of blah, let's call it, I already used A, let's call it C. T of C to be B, but we also know that's U transpose U C. So basically, we want to solve for C here. And we can do that, right? We can multiply on the left by U transpose U inverse again. And we get that our C here is U transpose U inverse times B. So if we plug in the m by n matrix, and remember, you can check that this is still m by n, because we know this guy is m by m, and we know B is m by n. So if we multiply those, it has the dimension m by n, so we're good to go. So if we plug in U transpose U inverse times B into our linear transformation, we end up with be back. So that's the definition of being onto. So T is onto. That's great. So there's some good techniques to show linear transformations are both one-to-one and onto.